I'm pleased to have with us today Dr. Siegfried Glenzer, who is the recipient of a recent E.O. Lawrence Award and is professor of the High-Energ Density and Division Director at SLAC National Accelerator Laboratory. He joined SLAC as a distinguished scientist in 2013 to build a new discovery class program in exploring matter and screen conditions using high-powered lasers and the world-class LLNL coherent light source X-ray beam. Before joining SLAC, he held the plasma physics group leader here at Lawrence Livermore National Laboratory for 12 years, where he led the first inertial confinement fusion experiments on the NIF ignition on the NIF. He has also been visiting lecturer at the University of California, Berkeley, and he is the individual recipient of the American Physical Society Excellent in Plasma Physics Award in 2003. He also won 2 DOE Excellence in Publication Awards and 2 Science and Technology Awards. In 2004, he received the Alexander von Humboldt Senior Research Prize and spent a research and teaching year at the Universität Rostock at the Deutsche Elektron Synchrotron in Hamburg, Germany. Since then, he has been the host for 2 Alexander von Humboldt Lenin Postdoctoral Fellows, 2 Lawrence Postdoctoral Fellows, 3 Peter Paul Ewald Fellows, and has supervised more than 30 postdoctoral scientists both at Livermore and SLAC. He authored and co-authored more than 400 journal publications, and he's published the textbook Plasma Scattering of Electromagnetic Radiation with Frula himself, Wilhelm Schaffert, and he is a fellow of the American Physical Society. So the talk will be recorded, so if you're comfortable with that, please log off, and please enter any questions you have in the chat field, and I'll read them at the end of the talk. And also just make sure everybody's aware this is an unclassified talk, and there are people outside the laboratory. Otherwise, I wish to extend a warm welcome to Dr. Siegfried Glenzer, and I look forward to hearing the talk. Thank you.
All right, thank you for the introduction, Paul. Good to meet everybody this morning. Of course, I don't see you, so hopefully this goes all right. So this morning I talk about exploring the most extreme conditions of matter with ultraviolet X-rays. And you can see in the background our accelerator at SLAC, National Accelerator Laboratory. Here we produce the world's brightest X-rays, and this is of course the theme of this talk. However, another big X-ray facility is of course at Lawrence Livermore Lab. I worked for 19 years as a postdoc and then moved up the ranks. Of course, this is the other big X-ray facility, and I'm still closely engaged with the program, and I'll show you data about it as well. All right, so when I came to SLAC and Stanford, the idea was really to think of our field of high-energy density science as its own field of physics. And what we wanted to study were basic plasma processes, extreme matter conditions, and material science from a basic perspective that is relevant for fusion science. Now, of course, all these themes are very challenging and are very exciting to work on. For example, in basic plasma science, we want to do experiments that we can test particle and cell simulations that predict novel accelerators, in particular study instabilities that lead to high-energy cosmic rays. And of course, the particle and cell simulations are first testing with experiments. There are issues of convergence and issues of large-scale simulations where you have to make approximations, and it's of course super interesting to do experiments, and I'll show you examples of that. In extreme conditions, you're interested in studying the conditions that approach burning plasmas, and of course those are extremely dense systems, and I'll show you many examples here. And here our goal is to test the density function theory. That's important for alpha stopping and for plasma heating, simulating burning rays. And the issue with DSC simulation is the exchange correlation function, which has normally been tested in solid-state physics. However, there are better functions out there for warm-dense matter and for hot-dense plasmas, and I'll show you an example of how we go about those. And finally, in fusion material science, the big challenges are the atomic interaction potentials that are used in molecular dynamics simulations. And just to give you an example, when we studied the melting of tungsten, and we had people making simulations for us, we asked them, let's do it blindly. We show you the data after the simulations. And when the simulations came in, the melting times weren't even in the ballpark. The predicted 700 picoseconds, and we found melt times of 20 picoseconds after laser heating. And of course, our collaborators are pretty competent, so what they did, they looked at other interatomic potentials, and they found one that actually nailed the data. So in that sense, it's really important to do these experiments and to make progress to testing our models that then are used to predict even more extreme conditions. So all this works well. And as I told you in the beginning, I will talk about LCLS experiments, and I will talk about NIF experiments, and of course there's a lot of success, and high impact publications came out here in 2020 to talk about the new methods to measure visibility of species, in this case carbon and hydrogen. And of course, we started this off 2 years ago with diffraction. Now we do this X-ray Thomson scattering, and this new paper out here. A lot of this talk will be dedicated to that. MEC has also been used to study structural evolution of glasses and liquid silicas. And then, of course, there's the NIF Discovery Science allocation, and Andrea just published a paper in Nature where she studied conditions that are important to the interior of white dwarfs, and I will talk about this also in more detail. Federico published this paper together with High-Energ Park and the collisional shock collaboration, and they have actually demonstrated the first order Fermi acceleration process in the laboratory. So all this is pretty exciting, lots of high impact papers. And of course, that's why we are thinking of our field now as its own field in science. And the challenges are listed here. We want to explore material and matter and plasmas at pressures above 1 megabar. That means you have to understand degeneracy, strongly coupled plasmas, non-ideal plasmas, radiative and relativistic plasmas. And of course, one of the big goals of our field is to create a burning plasma to create ICF and maybe eventually fusion energy with compressed matter. So, of course, these are exciting times. Just a couple of days ago, there was another Newton record on the list. And so my understanding is that the pressure that was achieved was above 300 gigabar and 150 kilojoule of fusion years, so which is about 10% conversion from lasers now to fusion energy. So which is quite exciting, and all that happens when you start as a liquid cryogenic DT and you compress it along a path to get to this point. And I think there's no lot of excitement in the field to push the boundaries further. So let's just compare this real quick. So let's compare to a jet plasma. So magnetic fusion plasma is about 0.1 gigabar. And actually atmospheric plasmas, because they're high density, they get to pretty high pressures. It's quite interesting. So there was this APS and what I talked by Peter Brüggemann. So it is interesting, but still this is really the most extreme case where we want to go. And of course, we've done some very cool experiments, and one of them is shown here. So we start to compress about 2 megabar in this regime, 200 gigapascal. And there's this paper by Dominic Krauss, and actually what we discovered was diamond rain. And because its connection to Neptune, that has received extremely wide public attention. That discovery was on CNN News and was picked up in some at National Geographic. And by close to 1,000 websites that people talk about mining diamonds on Neptune and they want to sell it. But why is that important for us? We know that from NASA observations that Neptune emits more radiation than it receives from the sun. That means there's an internal process going on that generates heat. And the idea here of this model is that we have carbon and hydrogen in the mantle of Neptune, and they're no longer miscible at high pressures. That means that carbon is forming diamonds, maybe big ones, and they gravitate to the core. And as they move through the planet, they generate friction heat, and that's the idea of what we're observing here. So it's pretty exciting process. There's still detailed modeling that needs to get done, but it was pretty exciting to see this data. So then we pushed it a little further, went up in pressure and density, and actually at that point we reached conditions on the interior of bone dwarfs. And actually bone dwarfs are some very recent objects. They were first discovered in 1995. And of course, these are important to determine the total mass of stellar systems. Actually, recently in VSET 229b, there was also the potential of a life-carrying super-Earth in the brown dwarf binary system. So here's an example of a brown dwarf passing by another object. So it's quite cool to study this type of material, and the reason is that there's dynamo activity, which is much stronger than predicted. That means the conductivity conditions inside the planet are different than all our models are saying. And we happen to study these conditions, and I will show you much more about this at the very end of the talk. But what you can see here is an X-ray Thompson scattering signal in the collective regime, and you see actually two plasmons, a downshifted and an upshifted plasmon. And the upshifted plasmon can only occur if there's energy in the system. So that theme will come again. So just remember that when a photon interacts with matter, the photon can always give momentum to the material, and that's known from the Compton effect since the 1920s. However, if the system is hot or it's in the one-length matter state, also the inverse can happen. That means momentum can be transferred to the photon from the plasmon inside the material, and that's why the intensity ratio must be inherently temperature sensitive. And indeed, it's simply reflecting the Bose function, so it's E to minus h nu over kT. So this is a way to measure temperature from first principles. And once you know that, then and you have an estimate of the conductivity, then you can really test your models. And as I said, we will come back to this later. So this was a big success. I already mentioned that we also studied white dwarf condition within the NIF discovery science, and of course this is pretty important for to understand the lifetime or the age of certain galaxies. When the sun stops burning, it just falls into a white dwarf, and then there's a hot ball that sits there, emits radiation, and slowly cools off. So from the light curve, you can then infer the age of galaxies when you look at them with a calibrated measurement detector. So people have done that, but people have done more about this. Let me first tell you how we do this experiment. We do it in the backlighting mode. You see here a ball at the center of a NIF photon. Then you have zinc helium alpha X-rays to backlight a spherical shockwave that's converging on the axis. And here you can see the shockwave going along. This is time, this is radius. So now you have two measurements. There's the velocity simply from following the trajectory. You also have the density from the attenuation of the X-rays to the material, and now am I still online?
I can hear you, Siegfried.
Okay, very good. Okay, there was some interruption here. Okay, very good. So we get the pressure. Now we can plot the pressure as a function of compression. And actually, what we see here the data. These one were published by Tito 2 years ago. This one from Andrea last year. And you can see that theoretical models that include the detailed atomic structure can agree very well with the data. So we have now a system, an equation of state that is well tested against experiments, which is of course important to model our white dwarfs. We also see that simpler atomic atom models like this one here is not agreeing well with our data. All right, so why is that so exciting? So it's not only cool to look at the age of galaxies. White dwarfs are also the progenitors to type 1a supernovae. And of course, they have been used as standard candidates in the expansion of the universe at 2011 Nobel Prize. That was giving rise to dark energy. That means that the expansion of the universe is accelerating. So why are white dwarfs standard candidates? It's because they're burning the pictonuclear limit, and that means it's only density dependent. And when some mass is accreted to a white dwarf, the white dwarf goes off and starts to burn again and causes a supernova. and they always start in the same way and explode. And that's why they can be used as standard candles, and the burning, of course, carbon, as most of you know. So this is an important area for white dwarfs. So, and the connection with SLAC is not only the experiment and the X-ray diagnostics and X-ray capabilities that they're using, but there's also the Vera Rubin Observatory, where we're actually installing the world's biggest CCD cameras to make a survey of the southern hemisphere. And there we will, of course, try to observe all the supernovae that go off, and also look for gravitational lensing. Those are studies of dark energy and dark matter. So there's a very nice connection here. So let me talk more about SLAC. Of course, most of the X-ray experiments are done using the LCLS. This is essentially 2 mile long atomic scale camera with femtosecond shutter speed. Of course, photon energies are now, most of the experiments have been done in our field at around 10 kilovolt, but very soon it's at 25 kilovolt. X-ray pulse length is now below a femtosecond, so it's in the attosecond regime. Most of our experiments are done with 50 femtosecond resolution. Typical benefits here of 0.1 to 2%. However, I show you that we can do much better. It takes some effort, but it's worth it, and it's an exciting new development. Of course, repetition rate is 120 hertz, and that's where that's mostly relevant for us. That's where we get the high energy X-rays. The 1 megahertz capability that is also being built up may only be used in a minority of the experiments. Of course, the machine length is roughly 2 kilometers, and we've seen this before. This is a annulator hall. We have a high current electron beam going through the alternating magnetic field, so that the electrons start to wiggle. They emit radiation. Now the current density is so high and the emission is so strong that the emission is actually modifying the electron beam itself, forming into microbunch, and then all those microbunches are starting to coherently emit radiation and producing the world's brightest X-ray source. So what I said is the X-ray regime. You can see this is how an annulator looks like, and it's like the distance here is about inches or a couple of centimeters. However, in the frame of reference for the electron beam, which is going at 14.8 GeV, of course, this distance becomes of all angstroms, and that's why you have angstrom radiation or hard X-rays. So it's all cool. This was 2009. And then we switched on the machine. Of course, it was the brightest X-ray source on the planet. So it was many orders of magnitude higher than synchrotrons that were operating at that time. And of course, others also switched on their own free electron lasers, and Japan, for example, and flash. But then for a while, that took the peak brightness records from us. And then we had a paper in 2015 with Luke Fletcher about self-seeding, and that's the highest peak brightness point that I'm aware of. So I think this is still the world record in terms of peak brightness, and it does matter for our field. The peak brightness is essentially the parameter to turn signal to noise of all experimental data in dynamic compression. All right, so LCLS is a user facility. It operates 24 hours a day. It's 95% beam availability. It's open to all of you. You can all write proposals, and you get peer reviewed, and you have a chance of access. So this is how it looked like 10 years ago. This is how it looks now. By now, we have replaced the annulator with a variable gap annulator. So now we can change the gap in a way that we can approach 25 kilo electron volts. Operation has begun in September 2020, and we are hoping that by September 21, or maybe later in the fall, we will actually demonstrate 25 kilo electron volts. On the left-hand side, we also see the annulator for the megahertz capability that is also being built. So this is a most recent picture, and of course, this came about in a big collaboration. I should probably mention that a lot of laboratories play important roles in putting LCLS-II together and enhance the national X-ray capability. But the bottom line is that for us and for our field, it all comes together at the matter in extreme condition instrument and the MEC target chamber, which is a Titan or a Titan target chamber. So we know it's been a very successful chamber that's been used in high-power laser experiments, and of course that's what we're doing here. We're bringing together the world's brightest X-rays with high-power lasers. And for those of you who have not been at MEC, this is a little video that here it shows the entrance. You go inside into the tunnel, and then you go underground. And then you can see people bringing up an experiment. It's actually cryogenic jet experiments because that's why there's a scaffolding. And here you see our beam scientists and collaborators bringing up X-ray detectors and spectrometers. So I told you here we are connecting X-rays with high-power lasers. The capability of those lasers is very moderate, but it's still exciting to do science here because the X-ray capability. So we have moderate short and long pulse laser, as I said, and we can use our X-ray beam. We can focus it, and we can. Here's an example of 10 micron focus. We use barium compact lenses. We actually shown in most standard experiments is 1 micron focus, and we can actually get it down to 150 nanometers. So we have extremely high resolution. You can also produce multiple pulses. Here are 2 examples. I will address this in a second. Just want to mention here that we do most of our experiments with 50 femtosecond pulses, and we can measure that simply from the loss of the electron beam, energy loss of the electron beam, that of course then goes into X-ray photons and determines the pulse length. So as I said, this is our facility, and we have a strong R&D program to do first-class science with moderate laser capabilities. And here are some examples. So as I said, this is the fastest spectrum that was done earlier. Since then, we have developed seeding to put more photons in a more narrow X-ray bandwidth, and that's how we get the high peak brightness. We then started to work with our accelerator people, and LCLS is a 3 gigahertz instrument, so we can fill up to 8 buckets with electrons, and then we get them all to lace. And here's the first demonstration of that. And this is a so-called pulse train. So it gives you 8 pulses down to 350 picoseconds. At the moment, we've demonstrated, I think, 1.2 nanoseconds, but the people are working hard to get it to sub-nanosecond time delays. And of course, this is important because once you have this capability, we can study material as it progresses through the high energy density science phase space that I showed at the beginning. And that means is that your experimental data are no longer dependent on the details of the initial conditions. So if you study a material with defects, the defects will always be different from one target to the other. But now you can actually study it for one particular defect, how it behaves as you're compressing a heat. The same is of course true for other targets that have unique initial conditions. So we are pretty excited about this, and actually people, collaborators in Sevilla and Livermore also think that this is important, and they have brought us the Icarus detector that allows us to start off experiments with 4 pulses, and Ariana Wiesen and her collaborators have already started to do some experiments, and there are more scheduled later this year. Of course, as I mentioned in the beginning, we are dependent on having good simulation capabilities that not only give us theory for the experimental data, but also help us to design the experiments. And Federico Piusa is running this effort here at SLAC, and he has shown the simulations that use big computers to get this done. And actually, it's quite exciting that they discovered a new instability, nonlinear instability that was presented I think yesterday by Ryan Peterson, and he actually won the poster award at the NIF XRTS user meeting. So this is quite exciting work that's going on. Finally, one more example. This is the novel terahertz capability that we have been developing. I will show you some of the data from Zhizheng. These are data from Ben Okai, who led the first successful MEC experiment. This is new capability, and that was actually the first experiment during the pandemic. So it was very challenging. People were with masks and social distancing and only reduced manpower, but he got it to work. So the R&D program is vital and is progressing well. And let me show you how we put it to use. So, of course, you have a target holder here somewhere. We put X-ray detectors around it. As I said, we have like gigawatt laser powers, so which is still remarkable because it means that every human on Earth will hold a laser pointer to the same spot. This is about the power that we put on those targets, and then we have detectors around it. So the X-ray beam is coming in. Oh, sorry. So of course, let me first tell you that we are using this to compress material, to isotope heat it, and here's an example where the lasers ablate materials, and then the compression, of course, is understood. So Newton's third law of actio equals reactio. So now we use our X-rays, we fire on our target, and you can see the signatures in the detectors. Here you have the Bashir rings, here X-ray Thompson scattering, forward and back scatter. You can then put all this information together, and for a cold aluminum target long per hole, we recover the structure of aluminum just like in a textbook. Then, of course, you do pump probe experiments. That means we heat it, we compress it, and we see first the compressed solids, and we see the phase transition, and then we measure the conditions in bonded matter. So here's an example of when we compress plastics. That was a study that Dominic published just a couple of years ago. And long per hole, when we use a shaped laser pulse, we actually see the diamond 1-on-1 diffraction peak. And that's made out of, the initial conditions are plastic. So they're shown here. This is our ambient condition. And as we are compressing, we reach a certain pressure state at low enough temperature, so it does, that we get the right conditions. You can see the diamond 1-on-1, and actually as the material falls apart again, you can see that the diamond, this compressed diamond, and falls back to ambient diamond. So pretty exciting. And here's what we believe is going on. You have the ambient polystyrene. The first rocket rips it apart, and then the second is increasing the pressures further, and then carbon and hydrogen is no longer miscible. And then what that means is you form diamonds, you also form mixed regions, and very likely you also form metallic hydrogen where you only have hydrogen. So it's pretty complicated. Of course, this is still under investigation in these simulations. So then we moved on. Actually, in December 2020, again, this Dominic, as a PI, he performed a remote experiment at MEC with mostly people in our team, local people here, actually doing the work on the ground, and the people were communicating through the beam time to get this done. And what's exciting about this one, now we use from 2 species to 3 species. And we add oxygen, you still see a very strong 1-on-1 diamond formation at the right conditions of 2 megabar. So you can make it very complicated, and of course this is new discovery that just came about. So what we do with this data, we test our equational state, and we test our understanding of phase transitions and of high pressure phases. So this is the range that we actually see diamond formation. And if you were just going along the Hugonio, we actually never saw it. There are some early experiments that people have seen it, but that's probably not because of a miscibility effect. That was probably of a long time effect on the experiment. The hydrogen was just leaving the system. So it's pretty interesting. So we got it only into these in that phase space. But what is the big weakness of all this? The pressure, we got it from VISA, but there's no independent temperature measurement here. It was inferred from modeling and from some of the structure factor measurements. So one of our goals was actually to start developing first principle temperature measurement that works in the one-dense matter and dense plasma. So somebody needs to mute his phone. All right. So here's our development of first principle temperature measurements, and we do it with X-ray Thompson scattering. Most people call it IXS, and this is like, the reason is, well, they call it that way, is because of very small bandwidths of tens of milli electron volts. That means we come in with our X-ray beam, which is already fairly narrow, which is seeded to 0.5 eV bandwidth, but it's not enough to resolve a phonon or an acoustic wave. That means you have to clean it up further. We bounce it around crystals, and we get the bandwidth down to tens of milli-electron volts. And actually here you can see an example of on a test on diamonds that resolves the phonons. However, that comes at a price, right? To start the beam, that means self-amplified spontaneous emission of radiation, gives you 10 to the 12 photons. If you seed it, you're down to 10 to the 11. Now you have to monochromize it, now you're 10 to the 10, and you only get 10 to the 4 scalar photons out of it. So that means we want to analyze as many photons as possible. That means we build those huge crystal analyzers that cover a large solid range, solid area. And of course, then we have 10 photons roughly here at this analyzer. And then we focus this back to our detector, so we're down to 1 photon. So that system would not work in a single shot, but of course we were lucky and we developed cryogenic jets. They're shown here on the right, so it's a continuous source. We started with this argon. We shock compress it with an optical drive at 5 Hertz, and then you look at the data, and you can see here's the instrument function. You see how the experimental data grow out of noise. And that's a way for us to make this measurement work. So we needed like 10,000 shots to have a nice spectrum, and it's shown here. Those are observation. Here's a fit. And again, you can see that the shoulders have different intensities. It will become more apparent later on as another picture. But you can see this is again the principle of detailed balance. And that principle of detailed balance allows us to measure the temperature from first principles. So we not only asked you to trust us, we actually went to the European X-ray in Hamburg and we did an experiment where we studied the anacoustic modes in well-controlled temperature conditions that are actually, here's a solid diamond at room temperature, and then we heat it up to 500 Kelvin, sorry. And you can see that as the system gets hotter, the intensity goes up, just as predicted. So the theory is right, we trusted it anyway, but now we have an experimental demonstration, and that came out in scientific reports. 18 accounts, one of our students published that together with Emma McBride. All right, so now you have that independent temperature or first level temperature measurement. You can now use this to really nail the HED phase space. And here's an example that we plot temperature as a function of time. And you can see this for first demonstration, the quality of the data was fairly acceptable. All right, so this is a summary of the diagnostics that come about just by thinking about combining powerful lasers and X-ray light sources. And here's the temperature measurement that I just mentioned as a function of time. But you can see how the asymmetry is evolving. And it's fairly nice. So this is the iron feature. Putting this back into context, that means X-ray Thomson scattering is now fully analog to optical Thomson scattering. So when I joined Livermore, in 1995, I worked on ICF, and the first thing that during my postdoc I developed optical Thomson scattering in ICF plasmons. And we did forward and backward scattering, and it has since then developed and evolved, and Dustin, Fuller, and others are now doing this experiment at Omega, and actually now continue to be performed, or just starting up on NIF as well. So now that the optical Thomson scattering is established, we're now establishing X-ray Thomson scattering. So they actually get the electron feature done. We can measure plasmons and Compton scattering, plasmons and forward scattering, Compton and back scattering. Hopefully I'll get time and show you a couple of examples. And now you can see here's the iron feature. We've done the collective one, the anacoustic waves, as shown here. Just recently there was another MDT experiment with Bob Naylor and Tom White and collaborating with our team, and they actually got the first signature of non-collective iron feature data as well. So we are now bringing this capability up to its full potential. So it's quite a success story. I mentioned the terahertz stuff already. I also want to mention the high pressure water data that Mungo first published. And actually what we've done, we use differential dynamic microscopy. So what you do, you look at the Brownian motion of suspension of suspended nanoparticles or nanospheres in in just regular water or deuterated water. And you can see we extended the viscosity data all the way out to higher pressures. And of course, this was a proof of concept, and is now being pursued with X-rays at LCLS, and that's also done in collaboration with LLE and people collaborating with Ariana that want to do this. So I mentioned terahertz already. Terahertz is a pretty important capability to study connectivity, and this plot kind of illustrates this. So if you only had optical connectivity data, and we use the one from G. James Chen that was published here, and if you then use this data and extrapolate back to the DC connectivity, you get the dash curves. So they end up somewhere here for sigma, some modeling. Independent of the modeling, you can see this here in these curves. However, you don't know if that's right. So now we have terahertz data that just recently, the paper was recently accepted, and the terahertz data are shown here. So now, if you have both sets of data, you can get actually the theory curves that gives you the right connectivity, and we know it gets the right connectivity because we have one 4-point measurement here for a solid foil, and to get the right answer. That means if you want to know your DC electrical connectivity, you better do it in the terahertz regime. And I think we heard a talk yesterday from Ben at the user meeting that demonstrated that. All right, so let me just show you this plot here. So there was a controversy on warm-lens aluminum, and I think for some people this is still ongoing. And there were papers published that the connectivity in warm-lens aluminum should really be this curve, and there was some pretty strong language in those papers, and we of course think that the papers are wrong. Here were our data and simulations, and those are published by Bastian and so on. And actually Ben just delivered this terahertz connectivity result. And so it's shown here, so it's pretty nice, but apparently this is where almost everybody agrees at this data point. So for some reason, this must be the point that is most easily measurable or most easily calculable. So of course, you need to go to higher temperatures to really distinguish between these models. But for sure, we can distinguish between that model and all of this. And that was published in a comment in Physical Review B 2 years ago, and I encourage you to read this. Essentially, what these theories use, they use the wrong structure factors. And we know that because you have experimental data that measure the structure factor, and that's why these papers were wrong. And also we clarify some of the typos that are in the literature. And so if you're interested in connectivity, this is a good paper to read. So of course, those papers are pretty important to us because it shows that HED science is X-ray lasers is a strong field, and it's advancing the science. So here are examples of that, and of course that has not gone unnoticed. It has sparked significant international effort, and I already mentioned that we've done an experiment at European Expert, the HED instrument, and of course this has been commissioned now 2 years ago, and this is a 3.5 kilometer long accelerator that it starts in the city of Hamburg and ends up in a different state of Germany, and you do experiments here in this area. So another competition is of course SLAC in Japan, and there was already much talk about the capability that is being built in China. All right, so I mentioned earlier that we have fairly moderate lasers, and of course all this competition coming up, we kind of use that to talk about a potential laser upgrade at CLS. And of course, I was also motivated by this report from the Academy of Science, opportunities in intense ultrafast lasers that Bill Buxbaum shared. And it pointed out that the US is falling behind with its laser capabilities. And it had, of course, a recommendation to build at least one large-scale open access high-intensity laser facility. The good thing is this has gotten a lot of momentum because we had all those workshops bringing the community to LCLS, building up the science case, and of course Donna came to MEC and also endorsed the idea to bring a petawatt lasers to MEC. And here's the example which we came up with. So we want to have a new cave where we have room for two target chambers. One here where the X-ray beam meets the lasers, and actually another chamber where only lasers experiments can be done on their own. And of course, we have to have a huge underground cave to hold all the laser capabilities. So that has been talked about a lot in these various community workshops, and has been endorsed, and we're pretty happy about this. The Rogers Brighter Initiative, and there was another CPP event that just came out. So this has gotten a lot of momentum, and we're presently preparing for CD1 this year. And here's what we want to build. We want to have a petawatt laser with 150 joule, 150 femtosecond that operates at 10 hertz. And of course, the idea is to produce bright sources of ions, neutrons, magnetic fields, and study fusion plasmas. And compared to the competition I mentioned earlier, this gets us quite far. And at the same time, we also want to build a compression laser to get further in compressed material science. And here we're talking about a kilojoule laser that shoots at a shot a minute. And of course, the idea is to produce extreme states of matter, near isentropic conditions, maybe get some unearthly materials. All right, so this all fits in nicely with the future vision. This is the accelerator. This is the far experimental hall sits. This is the present MEC is located. We will move a little bit further to the right and build a new cave for the MECU, for the MEC upgrade. It's called MECU. And actually, if we do this right, when LCLS becomes or expands even further with multiple under layers and instruments, we may have a chance to combine these lasers actually with another X-ray beam. So this is all exciting. So this is a future vision, but actually the future is already here, right? Because we now have 25 kilowatt X-rays, and 25 kilowatt X-rays allow us to measure the pair correlation function in a dynamically compressed system. And we have predictions for, in this case, for shock compressed aluminum, and that can only be done at 25 kilowatts because you need to cover enough inverse angstrom, inverse phase space, I think to 10 inverse angstroms in order to make an invert for the pair correlation function. Also, interestingly, if you go to higher energy X-rays, you get higher resolution in your X-ray detectors. That means you can push down the resolution potentially to 3 to 4 millielectron volts, by an order of magnitude that presently stand. Of course, that will be very important for studies of ion acoustic waves in dense plasmas. And finally, so far we have only done experiments up to 5 hertz at MEC and in a pump probe setting, lasers and X-rays. So, and we are now developing new targets, and hopefully we can take full advantage of the 120 hertz X-rays. At UED, at LCLS, we actually have just demonstrated 360 hertz, but at sub-millielectron volts in a pump probe setting. And of course, our goal is to push the limits here. Okay, let me give you one final example why all this is exciting and cool. You know, this is a measurement where an LCLS measurement where we done Thomson scattering in solids. There's a paper here that shows how that works. So this is now an X-ray Thomson scattering signal. You get the elastic scattering at 9.2 kilo electron volts, and now you get the downshift Compton feature. So the Compton feature is simply the X-rays give momentum to the electrons, and that's why they're downshifted in energy. And actually, this feature here represents the electrons that are in a metal. Right? This is beryllium, and it allows us to actually have a look at what is the best bound-free or what is the bound-free scattering spectrum or model to fit the spectrum. And we have two choices here. One is the Epsom rule. One is the RK rule. The bottom line is you can always get the intensity ratio right, but the fit down here is best if you use this type of normalization. And so now we felt like we are confident about our bound-free scattering model. That means those are electrons that are bound in the solid. Now we can also use it for one-length matter. So this is the same spectrum. I just moved out. This is 8,400. This is 9,200. So notice it shrinks a little bit. And now we overlap the X-ray Thompson scattering data from this. It was taken by Tilo and others. And you make three observations. First of all, the content feature is very broad. The inelastic scattering intensity has changed. And you can see the upshifted photons. And now remember what I said earlier, you can only get those if there's energy in the system. So, and of course, this is now a very sensitive measurement of the electron temperature. This is shown here, so Luke has done this bit. And you can see that since there's no bound-free scattering overlapping in this regime, that you get a very nice estimate of the temperature from this regime. And our fits show that the temperature can be inferred with an error bar of less than 10%. So those are states that are deep in the Fermi sea. And what is happening is, in order to give the photon some momentum, that electron has to be promoted down. However, if it's Fermi degenerate, it cannot go down because all the states are occupied. So only if there's finite temperature and there are states available is it possible for the electron to go down. And that's why this is a nice measurement of the electron temperature. All right, so this is quite a remarkable observation. We can now look at the Compton feature itself. The Compton feature is traditionally giving us the electron density. It's mostly sensitive to that because they are near degenerate regimes. However, in our case, we now find that the error in density is the largest because it still overlaps with a bound-free spectrum, and it's about 25%. So now we can also look at the ionization state, or at the elastic scattering that gives us the ionization state. And here we get, again, errors down to 10%. So we can put this all together, and we find this. So this is our Thompson scattering spectrum. This uses our S-sum rule normalization, so this is our best fit. And it actually does matter what normalization you take. So the blue data points are shown here. And if you use the other normalization, the data are lower when you plot Z, or the ionization state, as a function of density or of compression. So this is it's a nice finding. And what's particularly interesting is that Max Schörner, Max Van Hagen, and Ronald Redmond that did the density function theory, and they found these curves. Those are DFT results, brand new at 150 eV for this density range, and here for 100 eV, and long and behold, we observe much better agreement with the DFT if we use the right normalization. Of course, this is still work in progress. The analysis is being performed by Luke, Max, and Tito, and others. However, have in mind that this assumes a single temperature density ionization state condition. And this is a compressed barium, and that cannot be true for all times. There must be eventually gradients must occur, probably late in the experiment, where a single condition assumption is no longer valid. However, this seems to be pretty well fit with that assumption, as long as it's maybe close to peak compression. And what tells us that this is a good idea is the fact that we can also look at the forward scattering plasmons at very similar times. And again, we can do a fit. And what we find is that if you do this, if you do the modeling, that the 30-degree data agree nicely with our backscatter data. So that is validation that this procedure is doing very well, and it actually includes electron-ion collisionality in the Born-London approximation, which works pretty well in this case and actually overlaps with the DFT. So this is pretty cool. And actually, now, long and behold, if you're interested, here's what other people would predict if they use Stuart Pyatt or Eka Kröll. And of course, there may be some overlap, but essentially those models are not really applicable once you go to these very extreme cases. So, of course, probably I should conclude with this one, with this slide or with this vision, because what I feel is that HED is a really exciting, fast-moving field, and it's a really great time to be working in this field at this point in time. So when I get up in the morning, I'm excited to check my email, and I'm excited to think about everything because of all the opportunities that are being presented to us. And the last experiment that I showed to you, I talked about shock compressed matter, X-ray Thompson scattering, where Mike is actually now developing a new platform to get very homogeneous conditions for X-ray Thompson scattering conditions. And Amy is now is leading the new GigaBar experiment. And of course, what we want to do here, we want to study again conditions in the interior of white dwarfs, and we finally want to see this swing, which is predicted for liquid oxygen at pressures that we can access on the NIF. So this will be exciting to test. That test has not been, this observation has never been done, and of course it tells us a lot of how energy goes into shock waves. And this is a feature of L-shell ionization. This is a feature of K-shell ionization. And what that means, as you're ionizing the L-shell and the K-shell, you can put more and more energy into the shock. However, once it's all ionized, it all falls back, and eventually you reach just regular thermodynamic limits of rho naught of 4. So that will be exciting to see. So there's a Discovery Science experiment out there. I want to point out there's also the NIF diagnostics program out there, and of course George and Stephen are now building up the 3 omega and 5 omega Thompson scattering capability. The 3 omega Thompson scattering was already used in the collision shock experiment of FUSA. So now 5 omega Thompson scattering is next, and actually they just got it to work, and they saw the first time an electron plasma feature at 5 omega. This is just the very first piece of data, and of course this will be a very important tool to study whole worms. So finally, speaking of whole worms, one day I was preparing a lecture about fusion, and looked at John Lennon's book, and I saw all those pictures, these whole worms, this shield in there, and I was wondering, why are we not doing any experiments on the NIF that has LAH shield? So I asked Peter Ament and Denis Siegfried and others, and we came up with a proposal in the NIF Disruptive Initiative, and Alistair Moore is now the PI, and we believe that this is a very cool test. And what we believe what will happen here is that asymmetries will be reduced, and also the shields will provide more drive onto the capsule, and we get that's an additional 70 terawatts in drive. So it's very exciting, and of course all the physics eventually should come together, and we should be able to get to the goal of this field and to demonstrate fusion in the laboratory. And so it's exciting times. So I think we are taking full advantage of the field by using the world's largest facility. We can now provide insight into structure factors, mediated field generation mechanism, and the evolution of astrophysical bodies. We will produce fusion in the laboratory. I'm confident of that, and we may have to work hard to get there, but I think this program will succeed. And along the way, we will make new discoveries. Right? We already discovered the diamond vein. We have data on ultrafast melting. We developed novel accelerators. We've developed all types of new techniques that I've shown you, from X-ray scattering to terahertz to acoustic waves. And of course, the upgrade of the laser capabilities of MEC will be very important to advance the field and to continue to making these type of discoveries. With that, I should of course thank all the people that fund us, particularly the Office of Science, Fusion Energy Sciences, the FWP that has got all this started, and now of course we have other agencies that fund students and give us money, LDID money to advance the research. Well, thank you for your attention, and thank all my collaborators shown here. If I've missed somebody, I'm sorry. Those are always the hardest slides to make. All right, with that, thank you, and take your questions.
Thank you very much. A very nice talk. So please enter your questions in the chat field, and also I welcome everybody to unmute yourselves so we can give Siegfried a great big applause. Thank you. And we've already got a question from Eric Schwegler. It says, nice talk. Can you comment on any data science challenges needs when doing experiments on LCLS?
Yeah, this is of course an important question, and as I said, we now do 5 Hertz experiments. We will do eventually 120 Hertz experiments at high X-ray energies, but essentially, once you go to megahertz capabilities, the challenge is, of course, to have detectors that work at a megahertz, and there's a strong program, detector development program, to put these detectors in place. However, then those data need to all be moved to a supercomputer, and there's a collaboration with NIRSC, and there will be a connection made there to have some data analysis performed on a supercomputer. And for what it matters, there's of course a strong effort in machine learning to analyze this data without humans being, with humans just observing, not humans doing the work anymore. So that's being developed. It's of course the people that do experiments at a megahertz are pushing the limit here, and we will probably learn a lot from them and to advance our capabilities.
Are there any other questions? There's a question from Ivan Olejnik. This is very nice talk. I have a question concerning temperature measurements in shock compression experiments. What are the limitations of this technique in terms of materials, types, metals, insulators, transparent, opaque?
Yeah, that's a good question. So I think it becomes obvious. So if you look at this, so I told you that if you do a first principle temperature measurement, you must look at the intensity ratio of the Stokes and anti-Stokes lines. That means of the downshift and upshift with plasma. And they are only sensitive to temperature if the frequency shift or the energy shift is of the order of the temperature itself. So now here you see an energy shift of a few hundred eV. That means you can measure temperatures of a few hundred eV nicely. And this is shown here, you get the results. So now if you go back to acoustic waves, which is okay, shown here. So now what is happening is we're doing this on shock compressed solids. And the shock compressed solids are only of are less than 1 eV. The pressures are higher, they're megabar and beyond, but the temperatures are only 10,000 Kelvin or 5,000 Kelvin. So now you need to have an energy shift that is of the order of 5,000 Kelvin in order to use the balance. And that's why we need the higher resolution instrumentation to make this work. So, and that's why these systems work in terms of you have to bring the right diagnostic to the right problem. I think that this is what we have done here. So these experiments are done in argon. The goal is to do it also in krypton at higher Z, and I think that will actually be easy because higher Z species scatter more. The challenge will go to low Z species, particularly to hydrogen, and that's why the high rep rate comes into play, and we believe that we will have a science program to make that happen.
There's another question from Eric Schwegler. For the pulse train capability, not sure I understand how this reduces the effect of initial conditions on the target. Can you say more about this?
Yeah, so if you have say you have a solid and you have a defect at a certain location. So now, and you want to observe how the shock wave goes through and potentially gets amplified and moves further. So if you do this measurement with one defect or with a number of defects, and you want to make that observation. If once you have shot that target, the target is gone, and you have to replace it with a new target. So the new target will have that defect at a different location. The defect may have a smaller radius, may be deformed, may just look just very different. That means you can never put together how that system evolves because every target will have slightly different initial conditions. And that's actually true for almost all experiments in high energy density physics. Every NIF target is different. When people talk about I will reproduce my shot on this, they're always kidding themselves because the next target has a different dislocation density, has different craters, has different pits, and it's a different initial condition. So repeating the experiment can only happen in an approximation. And so for that reason, this capability is important because you're not dependent on the repeatability of the targets.
Here's a question from Ming Sheng Wei. Excellent work. Can you comment on developing and bringing advanced probes, like protein, X-ray, and particle to big driver facilities?
Oh, this is the right slide. So I think Chair may be actually one of the first things that we will bring to a big facility. So we've already done terahertz with laser probes and with FEL probes. So we've done that experiment at daily terahertz we produce in an accelerator. However, the laser probes can be transferred to an HED facility. And Ben has started to do this, and he has started to do this at Jupiter Laser Facility. So you shock compress material, and then use a terahertz probe to measure the shock properties. And of course, with more and more success of this technique, we believe this can also be used at, for example, Omega or NIF. So this is one of the ways that we can go there. I could give you more examples if you like. But we should probably do this offline.
So Ivan Olejnik would like to have your perspective on merging NIF compression capability with precise X-ray diffraction at MEC for LCLS.
All right, so there is already a diffraction capability available on this. That was actually developed within the discovery science arena by Ray Smith and John Eggert and Luke Collins and so on. So, and they're already taking great data. There was a Nature paper coming out just recently on shock compressed iron on NIF. So that capability exists. It does have much bigger bandwidth, and not as good, and the time resolution is of course different. So bringing an X-ray laser to NIF is hard. And I know people have jokingly spoke about this many times. But people have thought about accelerating electrons with lasers and perform have an underlayer there and do this type of X-ray diagnostics. I'm not sure if that's if we are really ready to talk about this seriously. So that's why at the moment what we are trying to do, in particular at the MEC upgrade, we want to build lasers that can shock compress ablators that are being used on NIF, like the diamond ablator, into the right pressure regime. That means you need to get to 10 megabar and beyond. Then we can study the physics of a diamond ablator with LCLS X-ray precision and test our models and learn what we can, and then feed the information back to the NIF programs.
Great. Thank you very much, Siegfried. It's been great having you here, and I wish everybody has a great rest of their Thursday. And let's unmute again and give another nice round of applause.
Thank you.